nanohub.org.
Online simulation and more for nanotechnology.
Okay, thank you very much. So today what I'd like to do is share some ideas that I've kind of been developing over, well, a while, but specifically my world tour of CRISP-related workshops. So over the last 2 weeks, I've been to 3 different workshops. This is the third. The first one was focused on hybrid simulation. I actually led that workshop in Zurich, Switzerland. And the idea there was to think about how do we experiment on structures in more novel and realistic ways. The second one was the Natural Hazards Research Infrastructure workshop in Washington, D.C. that was held Monday and Tuesday, which was an event with nearly 100 people talking about what do we really have to do to advance our understanding and our ability to be resilient to natural hazards. And that includes social scientists, that includes all the people here today. And both of these workshops have been developing research agendas. These are both last year's versions. The research agenda for hybrid simulation was developed at a workshop that was held in December of 2017 in San Diego. The outcomes of those discussions, and we're in need of updating that at this moment, and the 5-year science plan for the NERI community, which is a $62 million 11-center project. Actually, it's a little more than $62 million right now, but funded by the National Science Foundation to look at hazards and what are the different scientific advances needed to really make a difference here, to have impact. And the third being this workshop here. So we're talking about natural hazards. We're talking about how do our buildings, our lifelines, our bridges, everything in our built environment, how do we deal with the failures that we experience? How do we reduce the chance of that and improve, adapt, and accelerate recovery? So this made me think a little bit about going back to the origin of experiments, the origin of civil engineering experiments. So if you have a building, how do you experiment on your building? You can't easily test it in the lab. There's one laboratory in the world that can test a full-scale building, basically. It's in Japan. It costs about $1 million a day to run a test there. And it uses all the power from the city of Tsukuba, basically, to run that experiment. So if you want to run an earthquake test on a building, this is the only place. And obviously, it's still limited. We can't test a long-scale bridge. We can't test a super high-rise building. We have to develop new ways. Where did we start with this field? How did we start testing buildings? I mean, we all live in buildings, so we didn't experiment on them. We must have experimented on them somehow, right? Well, way back when, in the 1920s, we said, we need to start doing component level testing. We're going to test columns. We're going to test some assemblages. We're going to try to understand the behavior of that. And if we can test that, then we can design buildings. And we've been doing that for a long time, and we've been pretty successful, right? But it's still not as realistic as we could be, as we'd like to be. We clearly know this based on disasters that have happened, right? Hurricane Katrina, the entire city of New Orleans and the surrounding region, devastated. They're still recovering in some places from that event in 2005. Clearly, the testing that we were doing was not entirely sufficient. The thinking that we were doing was not entirely sufficient for these cases. The Fukushima nuclear disaster, again, a case where we were short-sighted in terms of being able to deal with, or what to even expect from such an event. It was a case where people knew that this could happen, but we didn't really want to believe it. That a tsunami this large could actually hit and cause that type of chaos. And thus, we didn't think too carefully about how to make our system resilient, our system of systems, really. So how else do we do experiments? Well, let's take I like our previous speaker, a bottom-up or a top-down approach. Well, if we want to test entire structures, what do? Well, we build them, truthfully. We say we know a lot. We may not know everything, but we know a lot. So we're going to build real structures, and then we're going to put them out there. And we're going to see when there's a natural hazard, what happens to them. So that's what we do. We build them. We see the devastation that occurs, and then we go on reconnaissance missions, and we find out what happened. What did happen, and how can we prevent that in the future? What are the things we didn't see in the laboratory or expect in the laboratory? What are the things we couldn't test in the laboratory? Maybe it was our own bias, maybe it was limitations, maybe it was just not thinking enough about it. And this is the way it's worked for the last 100 years or so, basically. Those reconnaissance missions then are meant to provide information, and this is the focus of our CRIS project, is how do we deal with the data that comes out of those reconnaissance missions. But those reconnaissance missions are meant to tell us information that we can use for new policy. Information to learn lessons about our infrastructure so that that doesn't happen again. We learn a lot of lessons. Some of that gets translated into policy, some does not. Some gets turned into design codes, some does not. We've been much better at that over the last, say, 25 years in terms of hurricanes and maybe 60 years in terms of earthquakes. Turning these things into actual codes and policies that do have a big impact on reducing it. But this is a slow process. We have to, first of all, build structures, and secondly, we have to wait for an event, right? So this path is not the ideal path for doing experiments and structures to make them more realistic, although it certainly is effective, right? So we know that there are, you guys have talked about this for a couple of days, so there are a number of infrastructures that we're trying to consider. It's not just the built environment, it's not just the building stock or the transportation network, but it's many. There's 16 sectors that have been identified, and there are a number of threats. This is from the Department of Homeland Security's report from 2013. I don't really consider earthquakes to be weather, but I think it's included in there. So what do we need to do in the future? Or what's one path forward that we could realize to make our experimentation more effective? That's what I've been thinking about a lot lately. So the technique that we've been talking about in hybrid simulation, in structural engineering, one technique that we've been talking about is real-time hybrid simulation. And the idea here is that we have a building. This is my building. We have a building, and what we want to do is test it. We want to understand the parts we don't understand. Nonlinearities, interactions, failure. We want to understand that. So what we do is we take out a part of the structure, we put that in the laboratory, but we can't build the entire building in the laboratory, so we take the rest and we put it into a computer model. So the dotted portion over here is my computer model. Put that into the computer, put the rest into the laboratory, and in the past we separately tested those. But that's not really realistic. So what we really need to do is test it in a big feedback loop. Okay, so that this is related to the idea of human in the loop, it's related to the idea of hardware in the loop, and some other things that people have named things recently. But the challenge here is that we have to put actuation into the system so that we can create the effect on that physical structure that the model would be, the rest of that structure would be creating. The interaction. We want to properly account for the interaction. We need control theory. We need an understanding of this as a dynamic system. We need to understand all the signal processing issues, the noise, the estimation, et cetera, et cetera. So we've been doing this for a while, and I have to admit we're still learning. This case right here is challenging to many people with one actuator. Imagine if we wanted to test a building and nearby structures in 10 different laboratories simultaneously, transferring all of that data, running all those models, running it at about 1,000 hertz in that feedback loop. So this is what it looks like in a typical feedback loop. You have your computer model sending displacements to the structure. You have the structure sending back forces to the computer model. The control, all of this is happening. Estimation, model updating, potentially all of those things are happening at 1,000 hertz here. We've been implementing this here at Purdue for many years. We started in around 2008, building a new laboratory to do this type of testing. This is one example, wind turbines. So if you want to understand how to reduce vibrations in wind turbines, you could use this type of substructuring method. And you could test your devices, your control devices, to reduce vibration in isolation, but within this feedback loop. Another example, we went to China, to HIT, and we tested this structure, and then we came back and we did real-time hybrid simulations to compare them to the experimental tests of the whole structure. We built a structure, a model of the structure. We did testing with damping devices in the laboratory, and we ran real-time hybrid simulations to do this type of method. Each of these has its own challenges, let me point out. This test was actually one of the first, but it's also one of the largest and most challenging in some ways. This was done at Lehigh University. This is a project from what was the previous version of NARI was the NICE project. And this was a laboratory, a shared use laboratory, where the entire laboratory was designed to do real-time hybrid simulation, even before we knew how to do real-time hybrid simulation. So the test specimen here, you can see Tony. Tony's about 6 feet tall, so he's not this big. He's 6 feet tall. This is a 40-foot tall structure in the laboratory that we were testing with 3 actuators that produce 400 kilonewtons each. And the idea was to test it as if it was part of the full structure with all the interactions present and do the real-time hybrid. And we were successful at that. But we've also gone in different directions. We've used real-time hybrid simulation to study wireless sensor networks. If you're doing structural control or structural health monitoring, you want to use wireless sensors because they're less expensive to install in your system. A lot of work has been going on in this area. And what we wanted to do was to look at fault tolerance of those. It's much safer to do fault tolerance experiments in a computer than it is to do them in the real world. So we went ahead and we used that same model that we had developed, and we focused on the wireless sensors and the fault tolerance. We could insert faults into the network, to the wireless network. We could insert delays into the wireless network. And then we could look at what happened to the control. We've also been working with some computer scientists at Washington University, Chris Gill, and developing what we call CyberMech, which is a parallel real-time hybrid simulation architecture that allows us to take a standard computer, standard multi-core computer, which is fairly standard these days, but not very expensive, and use those for real-time simulation of the finite element models and the controllers that we're trying to use here. This has enabled us to do a lot more things, looking at particle filters and model updating and such for these types of problems. But what I'd like to see is that we even think bigger. So we've here been talking about communities, city scales. Could we, instead of thinking about a structure and how to partition that structure and how to create such a feedback loop, could we do that at the city scale? Could we take out, say, the power grid, for example, replace it with a simulated power grid, but use the rest of that city and the rest of the data coming in from that city to do similar things, to do hybrid simulation? I don't know exactly how to partition this. I think that's going to be a very interesting learning curve to find out how to do that. But if we want to find out how disruptions really affect the real world and not how they affect our computer models, I think this is the only way to really do it, to learn from the reconnaissance data that's coming in. We've also been doing this and thinking about this for our Resilient Extraterrestrial Habitats project. So we have a project here at Purdue funded by the Provost's office to look at developing habitats on the Moon or Mars that are resilient. Clearly, resilience here is even more complicated, potentially, than it is on Earth. It might be a smaller habitat in a way, but it's got a tremendous number of disruptions. Temperatures, meteorites, radiation, and a lot of unknown situations that we have to think about. So we've been thinking a lot about how do you test these types of systems, how do you build a simulation capability for this type of system, and then how do you build resilience into it. And in closing, maybe this is a resilience framework that we've been working on, that we've developed, and the people who specifically developed it are not here at this moment. But this is a way of not only thinking about designing it to be resilient, but then having it produce resilient actions. A lot of the things we've been talking about here as well, to build this type of capability into our systems, the ability to adapt, the ability to respond and to recover quickly with constrained resource environments. So the future grand challenges that we face really require us to think about better ways to do experiments, to think about better ways to validate our models or to validate our technologies. And this idea of real-time hybrid simulation could be a way to do that. If we can understand how to plug in models or to plug in physical components into our models, then we may have some interesting opportunities for how to do better, more realistic experiments. So, thank you.
Any questions?
Shirley, you mentioned the cyber mech project with the real-time.
I knew you'd ask about that. Yeah. Oh, I'm just kidding.
But cyber is a draw. So do you see any challenges from the simulation side of the world?
The simulation side is huge. I mean, everything in this problem is huge, but what we're having a challenge right now, running a finite element model, when it goes nonlinear, combined with the controllers that are adaptive and doing model updating, running that at 1,000 hertz on a 24-core machine is what we're trying to do, and that's a huge challenge. We have to schedule, it has to be done in real time at 1,000 hertz or 2,000 hertz, depending on the experiment. So that in itself is a huge challenge, just being able to do that.
Have you tried running it on a distributed cluster, for example? Do the codes scale up to run on multiple machines?
Well, we'd have to rewrite the codes, I suppose, to do that. Plus, on a distributed cluster, we would have a lot more expense, and we would have a lot more, potentially, variability. In terms of getting it done in real time is important here. When you're trying to do control, you need real time. So if we were to go to the city scale, you would have even more computation to do, clearly. So, thank you.
Any more questions while the next speaker sets up the next one? Yes, you.
You're the next speaker.
You're the next speaker. Any more questions? Yeah, so how do you think of extending this framework to beyond the built environment? You're specifically focusing on that.
Well, I don't know what you mean by beyond the built environment. What I'd really like to do is to consider this for networks. I mean,
okay.
we have power grid, we have the water network, we have the gas network, we have all of these networks, we have the transportation network. Going in that direction is probably a next logical step.
Okay.
So, thank you.
Yeah, thank you.